for the introduction. You see here the title, development of sensors and optical filters towards detecting tissue damage during organ transplant. The Avik Sett, he did the work on the sensors themselves, and Filippos here has just started work on the filters. Doesn't seem to be wanting to. Now it's moving. Okay, quick overview here. So look at the needs for the organs. We're using optical techniques. Why? Oxygen and pH measurements, which is the main focus here. Measurement setup results, and finally some conclusions. Yeah. Why do we need to do this work? There is a shortage of organs for transplant. Many organs which might have been good get disregarded because the surgeons are not absolutely certain if the organ is good enough to put into the patient. And one of the problems is at the moment when they get an organ available, they put it in this cool box, they rush it to the hospital where it's needed. They do a couple of measurements and they think, okay, it's as good or not. We have a different approach now. This is from Erasmus Medical Center. Instead of putting it in a cool box, put it in an incubator, give it everything it needs, and do the measurements on that. And in particular, we're focusing now on pH and oxygen, but lactate and carbon dioxide are things we're also thinking of. So in this case, then we have more time to do measurements. We can be better sure that the organ is good. And in some cases, we won't even be able to improve the quality of the organ by keeping it in a very good environment. And also for the surgeons, it means they don't have to do an operation at 2 in the morning. They can just plan it for 10 or 11 in the morning, whenever it comes out for them. So these parameters, oxygen, if the organ is not functioning properly, not getting sufficient oxygen, then you will see a dropping in the level of oxygen. When you get this, you can get a buildup of lactate and hydrogen, so you get also a drop in pH here, and also CO2 accumulates. But at the moment, we're focusing on the oxygen and the pH for this work. So why optical? Well, we can get a good degree of selectivity. It's non-invasive, it's highly repeatable, highly reversible as well. We have to look at possibilities of photo bleaching, which could affect the signal you're getting. We have to minimize what cross-sensitivity there may be there. Trading off between time sensitivity and signal noise ratio. This is something we're not talking about here, but that's something we need to look at. And using a permeable layer so that the oxygen and the hydrogen ions can get into our device. And it should be flexible, so it fits very nicely to the organ. There's some early measurements we did on oxygen. This was using a polymer. And in this case here, we have, this is in the air. We put it onto, this is the kidney of a rat. And we just briefly interrupted the blood supply through the artery here. And we can see that our sensor was following it very nicely. It wasn't, this early work here wasn't completely calibrated here. You see, got a negative here, but it showed we could follow it very nicely. We also tried in blood, we see here. Again, in air, put it into blood. It's actually my blood that we're using here. And it got to this level here, which the doctor said it was normal. So my blood is normal, which is very nice. After a while, it dropped. Why did it drop? What happened was the blood was separating into plasma and red blood cells. The oxygen, the dissolved oxygen, was tending to stay in the plasma, and our sensor was with the red blood cells. So you have a good shake up, very scientific here. You see it jumped up a little higher because that shaking put more oxygen into the blood, and it carried on through the cycle. And the basic principle here we were using, which is called fluorescence quenching, fluorescence decay. We have a pulse here of blue light. We had a polymer in this case with ruthenium. And when ruthenium is illuminated with blue light, it fluoresces with red light. But if oxygen is present around the ruthenium, this destroys or quenches the fluorescence. So we can see here with a higher level of oxygen, we get a much sharper decay here. So we can just measure the level of the decay, and we have the oxygen level. And this works very well in the sort of oxygen concentrations we're looking at here. The pH measurements, we started with a hydrogel. This was a heart surgeon in Utrecht, actually, who was interested in measuring pH. That's a very good indicator of deterioration of the organ during open heart surgery. So when they disconnect the heart, they have to make sure that the heart stays healthy until it is then reconnected. So these were the two starting points here. And this is what we did. We actually moved across to a hydrogel here. And this is ruthenium here. And I won't go through all the details here, but basically we mix the ruthenium particles into this solution here. And we go round this cycle here. And we get this film here, which is a hydrogel containing ruthenium. And it is also a porous hydrogel, so the oxygen can get into it to get to the oxygen. Similar process here for the pH measurement, using the these beads, micro beads, dissolved in demineralized water. And it looks a little bit more complicated, but basically going through the same cycle as I showed for the oxygen, and you come out with another one here. And there's also fluorescence measurement. And as I show later on, it's very nice that for the oxygen, you get fluorescence in red, and for the pH, you get fluorescence in green. So that makes it quite easy to separate them. But then we thought, well, wouldn't it be much easier if we put both of these into one layer? And so Avik, he went on, got to work on this, and see if I can find the right. This is the top one here. This is the ruthenium, goes through this to this stage here. The same process I just showed, but with the microbeads, and we mix them, and we just get this new thin film, which is able then to measure both oxygen and pH in a single layer. Basically, the setup, here we see the source, which is actually near UV light. You have the filter here. Here is the layer containing, what I just showed, the layer containing the ruthenium and the other particles. And you have two photodiodes here, one for measuring the green light and the red light. The filter actually we don't have yet, but that's coming. That's what Filippos is now working on. This was the measurement setup he was using, and he was having solutions with known levels of known pH and known levels of oxygen. And here are some of the results here. Here we see the pH peak here, very nice peak here. Not much happening here, which is where you would have the red. But if we start playing around with the oxygen, there was some cross sensitivity there, which we don't want. So what he did was he shifted the excitation wavelength very slightly, and now he's removed most of the cross sensitivity. And once we have the filter, then we'll probably be able to get rid of the rest. There are different approaches here we're looking at. We can just take the two intensities, but we can also take the ratio of intensities or the ratio of the delay. We're not out of that yet. We're still looking at what is the best and most effective way of measuring the two in a single layer. We did some initial experiments. This is on a liver. It's a liver that has been rejected, and it was rather noisy. We did manage to pick up a few things here, and part of the problems here is the setup. We were trying to hold it on the tissue here. It was moving, and you had whether putting a little bit more pressure, a little bit less pressure. But this is now we have to sort out this setup and make it much more effective. The filtering, so what Filippos is now working on, he's mean, he's only just, at the moment, he's just done the simulations, looking at stacks of thin films. The moment, probably silicon nitride and silicon dioxide, so layers with different refractive indices. And the reason why this is we have a machine where you can actually just deposit these going one to the other without breaking the vacuum. So this is actually a fairly effective way of doing it. But this is just only just begun. So hopefully, maybe in a couple of months or so, he can actually start making these filters and testing them. So conclusions, we've managed to make a bifunctional sensor detecting pH and oxygen. They've been tested individually, but also together. And we've removed most of the cross sensitivity. We had initial tests carried out on a discarded human liver, which was rejected for transplant. The Filippos is now on standby. If they have an organ that's been rejected, they call him and he goes down to Rotterdam, which is fortunately only about 20 minutes away, and he can do the experiments. And he's also looking towards the filters. And then I'd like to go back to where I began here, which is thanking you all for your attention. Thank you.